Hello and welcome to the Basics of Calculus. So this is the first video of the limit section of the course. So in this section what we're going to be doing is we're going to be exploring the limit really in its entirety. We're going to talk about how it applies to continuous functions, how it's going to apply to something that we'll call continuity, and how it's going to apply to what we'll call discontinuous functions. We'll also talk about limits at different places on a graph, such as going to 0, going to infinity, and the idea of asymptotes, or these kind of approaching a value that really tie in really well with limits here. So this video is going to be an introduction to the limit. We kind of already talked about this a little bit earlier on in the course. Just to recap, we talked about the idea that, we talked about the idea that math can either be discrete math or we can have continuous math. And remember, the idea of discrete math was really these distinct indivisible chunks, while continuous math, an example would be like y equals f of x equals x squared plus 2x, where we have some output as a function of some input. And discrete math, an example would be some normal operation, 1 plus 5 equals 7. So we said that the limit was kind of like the video camera of math, that the limit took us from discrete math, these pictures, these snapshots at some point, to continuous math, kind of creating a video, a continuous loop. And this is a major part of what the limit does. Let me write that down. The limit is a video camera. And this is a major part of what the limit does. It takes us from discrete to continuous math, and it allows us to create this idea of continuity. And in fact, the idea of continuity itself, as defined in math, is defined in terms of the limit. But we want to talk about, really in a more rigorous definition, what the limit is. So we'll start this off with a bit of an example. So we talked about this a little bit. Say we have a graph. We have some input x and we have some output f of x. And the graph looks something like this. So this would be an example of a limit that kind of makes a little bit of intuitive sense. So if we take a snapshot of a picture in time using our discrete math, we would say that this is where x equals 10. And then we would say that this is f of 10, and f of 10 equals, let's say, 7. So f of 10 equals 7 at this time. Write that down here. So this is great. This is kind of an example of a discrete snapshot, because what this is say that we had our function was f of x is described by, and this isn't actually what this function is. I'll give an example where it does evaluate to 7. Say it was let's see, x minus 3 would be a good example. So say it was x minus 3, where f of 10 is equal to 7. So we can see here that when we plug in 10 for x equals 10, then we now get a discrete function. We now get, well, I shouldn't say discrete function, we get a discrete relationship. We get 10 minus 3 equals output 7. So we can see that by taking a function value at a specific point, taking f of x at one point creates a discrete relationship. And that's important to understand, because what we're doing here is we do have this idea of a continuous function, but when we take something at a specific point, it creates this idea of a discrete relationship. And this can kind of ruin how we want to talk about behaviors of functions, because we want to talk about behaviors at multiple points. Say we want f of 10, f of 11, f of 14. We want all of these points, and each of these are discrete. This is a discrete point. And taking it at the discrete point is going to give a discrete relationship, whereas we want to know the behavior across all of these. And so that's where the limit comes in. This limit says it is what the function approaches. So we'll write that, because this word approaches is very important. What the function approaches as the input approaches some value. So what does that mean? What that means here is that it's not talking about what the function value is at that point. It's not a discrete relationship. It's asking about behavior. This has to do with behavior of the function over time. And in a lot of cases, you'll see that it does end up being similar to what the function value is at that point, and that should make sense, but we're talking about behavior specifically. So we're asking what the function approaches as the input approaches some value. So if we draw our graph again, we'll draw it down here, and I'll actually draw a linear graph to represent our functional relationship. So f of x is equal to x plus 3, or sorry, x minus 3. F of x is equal to x minus 3. So it should look something like that. As you can imagine, it goes down here to the negatives. And so we'll get 10. It's right there. And we know the value is 7, but we want to know what it approaches. So how can we find that out? Well, the only way we know how to do that so far, because we haven't really been introduced to the idea of limits or any analytical techniques to solve them, the only way to do it is to take the values at discrete points. So what we can do is we can say, okay, I'll start here at 5. What's the function value at 5? Well, it's 2. So you can see f of 5 is 2. That's good. So now what we can see is we can continue this. We said we're approaching 10, so let's approach 10. Let's get to 7. What's the function value at 7? Well, the function value at 7 is going to be 4. So it's going to be 4 there. Okay, function value at 9. Function value at 9, I'll draw it in right here. Don't really have room to write it, but you can see it would go right there. Function value at 9 is equal to 6. What about function value at 9.5? Well, that's going to be equal to 9.5 minus 3. That's going to be 6.5. What about function at 9.9? That's going to be 6.9. And we could take this to be function at 9.99, so on and so forth. That's going to be 6.999, and so on and so forth. So you can see is that over time, the limit is talking about this process. What is it approaching as we get closer and closer to 10? So you can see as x gets closer to 10, what does f of x do? What does f of x approach? What number does f of x approach? And you can see here that we can see that f of x approaches the number 7. So we can say f of x approaches 7. And this should make sense, right? Because if you imagine, when I go along this line, I'm approaching 10, it's like I'm traveling up the graph. And I'm traveling up kind of in the direction of this arrow, and the closer I get to 10, the closer I'm going to get up here to this point, which is going to be 7. And you can see that that's kind of how that's going to work. We're going to approach 7. And so that's what the idea of a limit is. I don't want you to get confused by thinking a limit is just the function value, because we're going to talk about later on in this section, we're going to talk about how situations where that might not be the case, or situations where you don't have a function value. But in this case, what we want is we're showing how it approaches that singular value, okay? So I'll give you another example of something like this, maybe where it's more apparent that a limit isn't just a function value. Because a limit's great for use in functions, but we can also, because it's just a behavior tool, we can use it to analyze a lot more about a function, and this is kind of going to be a key detail in a later section on derivatives, and you might catch it when I start explaining this. So we're going to draw a familiar function, f of x equals x squared. This doesn't look a lot like x squared, but we can kind of see that it resembles it. So in this case, I don't want to know what the function value is approaching. I want to know, so say I draw a point right here, okay? This is my point where it's f of 3. So it's going to be equal to 9, right? So f of 3 equals 9, okay? So what I want to know here is I want to draw a line that is kind of what we'll call tangent to this function. I want to draw a line, and what tangent means is if I had like a circle, for example, it would be touching only at one point. That's that it's going to be perpendicular to kind of like the radius of here. It's only going to be touching at this singular point on the function. And you'll see why this is important a little bit later on. I'm going to erase that circle. But the way that we can draw this point is that what we can do is we can kind of approximate it using the function. We can see that if we take a point on the function right here, and we take another point down here, that we see a line that's sort of similar to it. And the further away we get, the further off our line gets. So like this line looks pretty close to the tangent line. That line's really not close to the tangent line, and this line's even worse. So these lines that I'm drawing here, these are called secant lines. They're lines between 2 points on a function, and they're supposed to approximate this tangent line right here, the tangent line to this function. And so what we're going to do is we're going to try to use those secant lines to approximate that using the idea of a limit. So what we'll do here is we're just going to use the rate of change formula. So the rate of change formula is the slope formula, and we talked about this in the prerequisite video. So if you don't really have an idea of how that works, go back and watch those videos. But the rate of change, the slope, m, of this secant line is going to be y2 minus y1 over x2 minus x1. So that's the slope formula right there. And so I want the slope kind of centered around this point, okay? And we're, just for simplicity's sake, we're only going to find the slope of this secant line and the slope of this tangent line. So my question then is, if this is the slope of a secant line, how can I get closer and closer to getting a tangent line? How can I better my approximation? Well, what I can do is I can actually take a limit, because remember, a limit is this idea of approaching something. So what I can do here is I can say that y2 is going to be this value up here. We'll call that f of x2. And we'll call this f of x1. Now, f of x1 is down here, and f of x2 is just f of x1 plus some delta x, plus some extra bit of x here. So really what we have is we can rewrite the slope as m equals f of x1 plus delta x minus f of x1, right? Because f of x1 is just y1, they're the same, and we can see that y2 is just going to be f of x2, and f of x2 is just going to be equal to f of x1 plus this delta x here. You're going to see why I did that in just a minute, why that's important. And so then we can divide by x2 minus x1. Well, if we plugged in x1 plus delta x for x2, we can do the same thing down here. So we'll get x1 plus delta x minus x1. So you see here we have actually, these can cancel, simplifies it, and we get that f of x1 plus delta x minus f of x1 over delta x. That's going to be our slope of this line. So this is the slope of the secant line expressed in two different forms. So I want to approximate the tangent line. So what we can do here is we can take the limit, but this time not with respect to x, but with respect to delta x. Because we want this line to get closer and closer to a tangent line. And so if we get these points closer and closer together, you can see that this line here, this line here has a greater delta x than this line, and this line has a greater delta x than this one. And you can imagine we get closer and closer, and the delta x gets smaller and smaller. We're going to get closer to this tangent line, the closer and closer we get. So we can take the limit as delta x approaches, well, what is it going to approach? We want it to get smaller and smaller. So this value, delta x, should approach 0. The limit as delta x approaches 0 of f of x1 plus delta x minus f of x1 over delta x. And so we can actually take a few discrete points here around this point 3, right? So we'll start out with x1 is at, we'll just say that x1 is at 3, that way we don't have to move it. So say that our x1 is here and that it's going up like that. So a nice way to draw this on a graph, as you can imagine, is the same graph. Here's the line, or there's a quadratic. This is going to be x1 equals 3. And so it's kind of like we're going from further away like that, getting closer and closer, which should work exactly the same according to what we just did. So x1 equals 3. And we're going to find this slope to get this tangent line at that point. And we're going to do that doing the exact same method that we just did for finding the limit of the function value that we did. So we're going to take this new function, this slope function, and we're going to plug in our delta x as our delta x gets smaller and smaller. So we'll call this our slope function. So slope of delta x. So what is the slope function when delta x is going to be, let's say, 5? So slope function, so slope of 5, meaning delta x equals 5. If we plug that in, we're going to get, okay, well, the function f of x, so this may be a little bit complicated. It's just analyzing two functions. So f of x, remember, is x squared. So let's write that in. This is going to be x1 plus delta x squared, because this is f of x, minus, we're going to have just x1 squared, and that's going to be over delta x. This is the slope function. So essentially what we've done here is we had one function, f of x equals x squared, and then we created a slope function to describe the slope of this graph, to describe the slope of this tangent line. And now we're going to analyze that slope using a limit. So we're taking the limit of this function, not this function. We could take the limit of that function just like we did before, but this is really to show you how limits are not just a function value. They're more than that. They're a better tool. So here, what we're going to do is we're going to take the limit of this as delta x approaches 0. So you start with delta x equals 5. So that's going to equal, we have 3 plus 5 squared minus 3 squared over 5. That's equal to, it's going to be 8 squared, so 64, minus 9 over 5. 64 minus 9, that's just going to be 55 over 5, which is going to equal 11. So that's going to be the slope there. So now, let's see what we can do. We're going to do the slope of 2. Okay, same process. Remember, 3 is going to stay the same. x1 isn't changing, so 3 plus 2 squared minus 3 squared over 2. So 5 squared is 25 minus 9 over 2. 25 minus 9, it's going to be 16. Oh, sorry. Oh, no, there we go. That's right. Okay, sorry, I thought I made a mistake. 25 minus 9, it's going to be 16 over 2. It's going to be equal to 8. So we go from 11 to 8, and this is the limit process. By the way, we're getting closer and closer. Delta x is approaching 0 with a slope of 1. The slope of 1 is going to be, we have 3 plus 1, well that's going to be 4 squared minus 3 squared over 1. So 16 minus 9, just over 1, and 16 minus 9, that's just going to be 7. And so you can see here that it goes from 11 to 8 to 7. And you would say, okay, well, why are we taking this limit process? Why didn't we just do the same thing you just did, except plug in 0 for delta x? So I ask you, let's plug in 0 for delta x. Slope of 0. If you look, we get, okay, just going to be 3 squared minus 3 squared divided by, well, delta x is 0. Oh no, we have a problem. Okay, so not only is the top 0, right? We have 3 squared minus 3 squared, but the bottom is 0. And this is a problem. We can't divide by 0. Cannot divide by 0. That's a problem. That's an error. And if you want to prove that to yourself, try to imagine taking something and dividing it 0 times, right? How many times can you divide something by 0? So let's imagine you have like pencils in your hand, 2 pencils, and you divide that by 2. How many times can you take away 0 pencils? Well, you can take it away an infinite number of times, really. And we know that the slope to this graph here isn't going to be infinite. We know that it does have a set value because it has to have a set value that's not infinite. Infinite would be going straight up and down. And we know it's not doing that. It's tangent to it. So we cannot divide by 0 here. And as we get further on in the course, we'll talk about really the solution to this problem where we don't have to solve it numerically like this, where we approach a value, but how we can solve it really using a really nice analytical technique. And that's going to have a lot to do with derivatives. But for right now, the limit is all we know how to do in order to do this. We just need to approximate it. So we could take the slope of 0.5, for example, where that would be really nasty to calculate, but this number would get smaller. And actually what you'd see is that this limit right here, as delta x approaches 0, it doesn't approach infinity. The limit approaches 6. For this specific case, you'll see that the limit approaches 6, and you can kind of start to see that 11 goes to 8, which then goes to 7, and that's then going to go down to 6, and that limit is going to approach the value of 6, and you can check that by plugging in smaller and smaller values. You could plug in delta x equals 0.5 into a calculator, delta x equals 0.1, and so on and so forth. And you'd find that the limit approaches the value of 6. So this is an example of where a limit really isn't just a function value, it's something that's much more useful than that. It's going to tell us about the behavior of the graph. It's going to tell us about the behavior of these functions when we can't discuss the behavior normally. Another example would have to do with asymptotes. It's really going to be the last example we're going to give for this video because the video is going on for quite a while now. But if you think about, for example, I draw an asymptotic function. So say I draw a function like that. So this asymptote is, we talked about this in the prerequisite videos, but an asymptote is where it approaches some value, but never touches it. But never reaches it. And so in this case, you could imagine, we won't actually do it numerically, but you can imagine taking the limit as x approaches infinity. So as x just keeps going and going and going, well, this function value doesn't have a defined value at infinity. Infinity is not a number, right? Infinity is not a number. So f of infinity does not exist, so does not exist. But what we do know is that if we take the limit as it approaches infinity, it will have a defined value. The limit as the function approaches infinity does have some value. It does exist. We can see that as it approaches infinity, it's going to be getting closer and closer to, say, this value right here. Maybe that's 2. So it approaches 2, and that limit is going to equal 2, because that limit is this idea of an approach. So this video, I know, had a lot of examples in it. It had a lot of kind of new concepts, especially this idea of a slope. If you didn't get this example, please feel free to go back and rewatch it. We will be talking about it more in more detail later on. So you don't need to completely get this example specifically, but really just understand that a limit is more than just a function value. It's this idea of approaching something. It's this idea of when some value approaches another value, what's the behavior? And the power of the limit really comes in not when we're talking about normal linear functions or things like this. The limit really in this case is just going to be similar to the function value. And we'll talk about that more later on. But the power of the limit really has to do when it comes to things like this, where we end in situations where maybe we're dividing by 0. So the limit is better here. This is really where the limit shines, where we're dividing by 0, or say we're getting to a point where we're taking f of infinity, where something is approaching infinity. We know that doesn't exist, and that's where the power of the limit comes in. It tells us about the behavior of something as that x value or as that input approaches infinity. And it's also important to know that the limits don't have to be used directly with the function for a function value. Like we said with the slope, they can be used with sort of outside functions, functions of functions. Like in this case, we had the slope function, which used this primary function as an input for it, and then we took the limit of that slope function with respect to a delta x. So I hope this video was helpful. I know it was a lot of information all at once. We're going to really try to dissect this information in later videos, but again, I hope it was helpful. Thank you for watching, and I hope to see you in the next video.